So yes. So basically, before starting Monte Carlo, we must know what is Monte Carlo method and why it is used in different part of sciences and mathematics. So basically, Monte Carlo method is a problem solving technique that uses random numbers and repeated simulations to understand complex systems like star clusters or galaxy clusters, etc. So, for example, we have a complex problem which can't be solved using one formula. Okay, so we simulate the system many times with some random values, random inputs, and find out what is the variation in statistics, and then combine that to find the best output for that problem. So, in simple way, if a problem is too complicated to solve directly, simulate it thousand or millions of times using the randomness and look at the statistics to find out the exact value. So first of all, for the similar case in mathematics, we have a problem of value of pi. Okay, so the value of pi is not accurately known at some ending decimals. So we for that purpose we will use Monte Carlo to find most accurate value. Okay, known in today's time. Okay, so after the basic concept of Monte Carlo, using the maths and all that stuff, using Python, that then we will apply this Monte Carlo method in simulating the star clusters. Okay, so first of all, to use Monte Carlo, we don't have any specific library. Okay, so it's just a mathematical or statistical method. So we have to just define some functions for Monte Carlo and use basic libraries like NumPy and Matplotlib. So I'll just import NumPy as np, import matplotlib dot pyplot pyplot splt. Okay, uh, okay, so now I'll just create a markdown generating pi using Monte Carlo method. I'll share a PDF with you. There was a school at Marinda House of Delhi University. So there they did the Monte Carlo method on dark energy simulation. So you can have a look to it. So similar stuff we will be doing for our star cluster also. So the thing they did in the Miranda house was actually verifying the previous research. So you can have a look to it if you know, because it uses Gaussian method and Monte Carlo both. So since we will do it by the end of this lecture, you will be easily able to understand what they have done, and you can also repeat it if you want for your purpose. So now, first of all, uh, so for generating the value of pi, we need a circle. Okay, so for circle, we need to create a circle. Also, then we have to put some random values onto that circle to find out the exact value of pi. How to visualize this now? So, for example, you have a bangle, okay, and you want to fill it, and you have to keep the rest of the outer side of the bangle empty, and you have to see how much times or how much values of the small balls. For example, you have small beads, circular beads, you have to put in that bangle. Okay, you have kept that bangle on the floor and you have to fill that inner part of the bangle with the beads. Now you just drop the beads randomly. Okay, you do not specifically pick a bead and put it inside the circle. You just have thousands or millions of beads in your hand or in some bucket or something, uh, in some container, and you just directly shower that beads onto that bangle. Now there is a probability, now some of the beads will bounce back and go outside the circle, and some of the beads will retain inside the circle. Okay, now those beads which remains inside the circle will determine the value of pi. Okay, for that circle. Now, more will be the beads, more will be the accuracy of pi. Okay, if we have less beads, for example we have just 100 beads, and out of 100 beads only 10 beads are inside the circle, and it will not complete, it will not tightly fit inside the circle, which means the proper shape of the circle, if that border or the bangle is removed, will not be defined. For example, you have just ten beads inside the circle, and you just take the bangle from there and put somewhere else, and now call a student or someone, your friend, and ask him what is the what these 10 beads indicate, which polygon it indicates. So those 10 beads can be some different regular polygon or irregular polygon also. But when you have millions of beads, so those millions of bead will don't have that much space to just randomly go inside it, fit inside it wherever they want. It will tightly fit inside the border of the bangle. So when you will pick the bangle again back out of that place, you will see a proper circle formed by the bead. So this will help us to maintain the accuracy of value of pi, for the value of pi. Okay, so this is what we will be doing, and I will be showing you how these values of pi varies if we increase or decrease the number of beads. So you can also take it as an example of a gas molecules in a container. Lesser is the gas molecules, more will be the distance between them, and more will be the gas molecules, less will be the distance, and the interaction will be more strong, and they will be much closer to each other. Okay, so we have to make a simulation where those molecules are very close to each other, so to get the accurate value. Now we have to define some random x and y values. So we will use numpy to define a uniform randomness. So we will define np dot random dot uniform. Then let's say we take the those x-axis from -1 to 1 with let's say 5000 values, with 5000, let's say. Similarly we make make it for y. We need actually a square. Okay, so inside that square we will create a circle. Okay, now we have to form a like circle. So for that, let's say original distance, which is basically, original distance means defining the radius. Original distance which means the radius square. Okay, so which will be is equal to x to the power 2 plus y to the power 2. This is basically the formula for the circle. Okay, now let's define the theta. Theta will be basically here as a 2D, which will create a circle. Okay, so let's say it is in some random values, not random values, in the range values, with the linspace from 0 to 5 times of pi. 5 times, I just randomly took this value, and with 3 to 1000 value inside that range. Okay, so I'll tell you what what this do if I change these values, or what this do if I change the radius also. So I define the radius to be 1 for now, and now a is equals to radius times numpy dot cos theta. This is basically the, you can say, the parametric equation which include those cos theta and the sine theta. If we take argument value, we have cos theta, a cos theta, a sine theta, where a is a radius. So I'm defining that thing, radius, and p dot
Sir, I
cos.
had a small doubt.
Yes.
Sir, original distance radius is root of x square plus y square, right?
Yes. So we have just defined it for now. I'll tell you, let me complete it. I will tell you what is the difference between the original distance and the radius I have defined.
Okay, sir, sure.
Yeah. So just a second, I just found out. Okay, so just a second, I just found out that my AirPods are not connected. It will create a problem for recording. Just a second.
Just please confirm with yes or
Yes,
no.
Yes, your
sir.
voice is clear.
Okay, so done. So I'll resume this part. So we have theta here, and then I'll just try to plot it. Figure, then figure size will be 6 by 6. Then PLT dot scatter. Scatter will be for those beads. These are those beads we are defining. So it will be X random and Y random with, let's say, alpha. Alpha is basically the transparency, let's say 0.5. And now we will plot. So as I told you, there will be more and more features you will see when we will be using matplotlib. Then A and B. So the this is basically those the thing we have the equation of a circle. Now I'll tell you, line width is equals to 3. However, we will not be using this. So there are two things now. The doubt that Huda has, this equation and this equation. Either you can use this thing, either you can use this thing to plot the circle. Okay, so I just wrote both of these. So I'll tell you uh, after the making the plot what is the difference. So basically, there is no difference because both of the equation, one is in the form of theta and one is in the form of that x and y, the Cartesian format. Okay, so you see, we have this circle with the beads into it. If I just remove this thing and then plot, it will plot it because it was just written for the sake of the equation. Okay, so here equation equation of a circle where this original distance is basically r square. Okay, r square. Okay, so it's not only a distance, it's a distance with r square, that is the distance to the power square. Okay, I know you know this formula, so basically it's this formula. Okay, the form of Cartesian. So basically this is what it is written. So I'll comment this out. So either you can do this thing, otherwise you can do this thing using by defining theta first and then defining the radius and then defining the thing here, a and b. Okay, so a is equal to r sine theta and a is equal to r cos theta, b is equal to r sine theta, whatever you can write here. So this is how you can create a circle. If we increase the value to 10,000 here, 10,000 here, you see there will be more beads here. Okay, if I just create it to 10, and this will now give me an error because the uniformity of x and y must be same. Okay, so both must be same. Okay, so there is an error. Why? Okay, now it's correct. So this is what I was saying. Let's say if we have 100 beads. So some of the beads are in the circle and some of beads are out. And when I will remove this reddish part here, the exact circle, this is for the sake of reference. If I just remove this, you can't be able to trace which of the beads are inside the circle and which are out of the circle. But when I just make it like 10,000 here, now you see Even if you remove this part, you will have the gap in this border, and this gap will trace a circle which with these beads, and this will be the outer part of those circle, and it will be particularly very useful to find out the pi value. So this is basically the visual diagram of what I was telling you about the Bengal experiment or something, that activity. Okay, so now we will be finding out the value of pi. So there are some things you need to keep in mind. So here for finding the value of pi, we will be using some formula, the relation, which is four times the circular pi divided by the square points. Square point is basically this square, the square outside the circle. It's basically the square, and inside that there is a circle. Okay, so we will be using that now. I'll write this thing here. So just a second. Okay, so just a second, guys. So just a second, guys. Sorry for this technical issue. Okay, now we will write a range. So basically, this is as we discuss here. So this is the square of these points from the center. So we will be using this also to find out the value of pi, because we need to know the distance of these random points, these x and y points, these random points from the center of the circle. So to calculate the distance, or to calculate the value of pi. However, we can use this also to define this circle also, but not to create any mathematical error. We defined this thing differently and this equation of circle differently. Okay, just for the sake of less error. Now this is basically the equation of circle, as you can see, and this will be considered just as a locus of these points from the center. Okay, which will be different for the different values. Okay, but whereas this is constant for this specific range. Okay, so this circle is constant, but the distance of these values varies for different points. Okay, from the center, those points are inside it. So this is the basic difference between these two equations. However, these overall these both equations are similar, but there is a very minor difference, that is x random and y random have many values, and different values have different distance from the center of the circle. Now we will define some circle points. Circle points means the points inside the circle, which is right now an empty or null value, let's say 0 for now, because we will be applying a range into it. So then say the square points are initially 0 when the experiment or activity was not performed in the Monte Carlo. Now for I in the original distance, which is the sum of the distance of those points from the center, those all distance, if I is less than equal to 1. Now, Now here, if we use this formula, which was a circle formula, we won't be able to define any element because it is independent of these random values. That's why we define this one more equation which is dependent on these values. So now we can able to define the function such that those values which are inside the radius 1 will be considered as circle points, and those points which are out of those circle will be defined as the square points. Okay, now circle point will be is equals to plus is equals to 1, which is circle underscore points will be increased by 1. Okay, those numbers. Okay, now square points outside that will be increased by 1. Now there is a formula. So main relation to find out the pi value. So we will consider it as a temperature value. Temperature value is basically the entropy or something you can say a standard reference which says how much concentration is there in that value. Okay, so how much concentration or you can say yes, the concentration is the right word, is inside the circle value, and this helps us to if we just append all these values, if we just add on these all the values, we will get the values of pi. So here is a relation where temp is equal to 4 times circle points divided by square points. Okay, now pi appends temp. Okay, so now here's a catch. We have not defined pi value. Pi is equal to pi values. Pi value is null for now. It doesn't contain any value. Now it will be appended by temperature, this temp. Now pi is equals to numpy arrays. It will be array. We will save it as an array. So that's why we defined just to make it sure. So it just have the similar data type. Now we have to also define a value now, which will be x. So we have to again define those values which will be dropped inside those bangles, which will be, let's say, x, which is initially null value. Now for now here we have defined everything. We need to create uh, we need to find out the value for the pi. But now finally we have to drop the beads. So we have to define a function to drop the beads, which will be for I in range. Now here will be the value of the beads that you have to drop. Let's say 5000 for now. X dot append I. Okay, so I will append this value of x. Now finally I will plot it and check what is the value of pi. Let's say x label. I'll define the x label as the number of points because it will be this x number of points, and plt dot y label will be the estimated pi value, and finally I will do plt dot plot with x as the those number of points and pi as the y, and now I will dot plot this. Now it shows okay, so I have to just do this thing. Then it says numpy has no attribute arrays. Yes, it doesn't have any attribute. It's a array. Okay. Now what's the error here? It must have same dimensions. Okay, so here is an issue. Here we defined our x random and y random as 10,000, and our original distance is also dependent upon the r random and y random, which will be basically of a dimension which is 10,000, because it is dependent upon r random and y random, and hence the original distance will be also of a dimension with 10,000. But now while plotting, we defined the x value, that is the x-axis, as 5,000, which basically changes the dimensions. Okay, so since pi was dependent upon this x original, so pi also got a dimension of 10,000 values. Okay, now we defined here x as 5,000, which is 5,000 dimensions, which mismatched, and finally we have a error. So if I define it as 10,000, now you see that we have a very good simulation. So basically what it shows here is, it shows the value starts from 0 for the estimation as defined here. Okay. And then when the beads were started pouring into it, the value goes from 3 to 3 point near to 3.5, and then all that. Once those values are filled, the number of points, the number of beads were inside around 10,000, you see the error, the fluctuation in the value of pi get decreased and decreased and decreased, and it is approximately now, you can if you can see here, it will be around 3.1 something. Okay, so more will be the value of the beads, more will be the concentration inside the circle, and hence we will get a good results. Now, so this is one case. Now we can also use this similar case for plotting it, the similar thing for the 3D sphere. Okay, using the 3D sphere also. So now we will do it for 3D sphere. It will be such similar code. The only thing will be we will introduce the x-axis also. Okay, so what we can do is, uh, let okay, so we have time. What if you guys try to plot the simulation for the 3D and take it as a homework, and we will discuss in the next lecture. But today only, the 3D also will do today only, because we have to learn SQL language. SQL is also one more computational language which is used in integration with Python. So for that, we also need some time. Let's say uh, we define a figure for 3D. For 3D, we have to use those subplot methods. Okay. So now let's say x is equal to figure dot, oh sorry, fig dot subplot 111, and projection. Earlier the projection was different, and now we will have a 3D plot using matplotlib. So this is why I didn't explain everything in the matplotlib, because now we will use the method of matplotlib to plot a 3D plot. So I'll just copy these things here from here, and I'll change it to Z. Now original distance underscore x random multiply double asterisk basically plus z random. Okay, now basically we have to now define the parametric equation for the sphere. So this you must know. It will be basically uh, cos x into sine y, and for the y it will be sine x and it will be sine x sine y, and for z will be cos x. Uh, Basically, x and y, just I spoke here, is not same as x, y, z we will be defining. You can like say it as a and b. So x will be is equals to cos of a times np dot sine of b, and here for the sine it will be sine, and for z it will be just cos a. Okay, now we have to also define it, define a and b before it. So there is something called mgrid. Mgrid help us to uh, plot u and v values, u and v from the equation of those sphere, which is here defined as a and b. So it will help us to like make our simulation for those values in the form of sphere. So we will use mgrid, numpy.mgrid. So you, so I hope it must be visible. So yeah, so let's say you have a grid. Okay, the mesh, basically it will be a double matrix. Okay, so it will create a matrix. If we have something like 0 to 5 and 0 to 5, it will create two matrix, two meshes, and it will look something like this. If we create 0 to 5, it will be a row with 0 values and then another row with the 0 values, and it will create till the 5, and it will create double matrix. It is actually the single matrix is known as single mesh, and another matrix is the another mesh, and then they have used indexing to find out some particular values here in the documentation. Okay, so we will be doing the similar thing. If I get some images here to show you, so you can see it is something like we will be doing because we will be having the 3D thing. Okay, so yeah, so I'll just write the code first, and then I'll then when it will give some visualization, you will get a better understanding. So let's say our range is our problem is for sphere, so we will be defining it as a within pi, within a range of pi. So I'll tell you it will be something like numpy dot pi, and then okay, okay, so just a second, there is an issue here. Let's say okay, so just a second. So I have some confusion here to define the mesh here. So I'll just go to the numpy here. So they have used something called J here. Okay. So we have also need to use this thing. So it is basically the numbers of point it will generate, I guess. So something like linspace. Because as I can see here, it has created -1 to 1, and inside in total it has 5 numbers. So I don't think j here is something like imaginary number. Of course it will create like those uh, values in total. So 1 2 3 4 5 values in total. Okay, so We'll try first. If we get wrong, we'll see. So basically, it's not something related to imaginary. It's just a syntax of the M grade. Okay, now we will create the similar thing for our another part, which will be B. We'll use comma here, and let's define the B in the same proportion. Let's say those values are in 100, in thousands. Now we'll define A and B as this variable. Okay, this part is done. Now we will create. There is something called there is a feature, something called wireframe. Okay, if I tell you what is the wireframe matplotlib. So it is something used in this uh, 3D plots. Okay, so it will create a frame for plotting the 3D plots. Okay, so now that we have wireframe and the parameters will be same x, y, z. So now ax scatter, it will create a scatter plot. We have to create a scatter plot for r random. R random will be r where is x, y, z. Then let's say alpha is equals to again 0.5 and color this time let's say is green. However, the 3D thing is not being much used in astronomy until required. So even in my part of astronomy, we don't use 3D much. So that's why I was just confused with this part of the mesh grid. But now it's when I look at the documentation, I just got to know yes, it this indicates something like lens space we use. So now we will create one more thing here. Uh, okay, so we have some error here in the mesh grid also. It says okay, so I just double printed this. Yeah, I guess it will not give any error, and I have to define a figure here. Fig is equals to plt dot figure, and I have to define the figure. Let it be with the dimensions. Let's say the sorry. Yeah, I guess. Yes, 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 yes. We have something here. Just a second. Yes, yes. Shit. Let's say 3,000. Yes, 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 yes. Yes. So we have finally the best thing here. Uh, okay, 1,000. Yeah. So yes, yes, we have. So there was an issue with the equation. Yes. Okay. Okay. So there were many issues. Pardon from my side actually. So it actually becomes an oval type thing. Oh, I'll just read this part. So yeah, you see here. Now we have a sphere, a globe, something like that, and we have the grid. Since the equation of a sphere was wrong, it should be cos B, not cos A. Yes. Oh, so I'm regretting now on many things. So okay. Also, there was an issue with add subplot. It must be add subplot, not subplot. Plus, it should be wire frame, not wire fame, and it should be z np dot cos b, not cos a. Okay, for the correct equation of a sphere. And so we have the similar thing here. and we can also define these xy labels if you want. Now finally we make the similar plot like this for our 3D. Now it might fluctuate more or less depending upon our read values. So we'll just fastly define it and then we will start with the second thing. So it will be sphere. Let's say sphere points is equals to 0 and cube. So basically we will verify if we get the similar answers or not. Also the pi will be this for I in origin distance underscore. If I is less than equal to 1, since we have defined a generalized thing here. Okay, so I'll just first turn off this notification. And sphere. Okay, so I'm still regretting that we were stuck on the spelling mistakes and the bad mathematic equation. Okay, so we spent a lot of time on that. Now, for the 3D, we have it 6 times. So we have to write the similar code here. Just we have to change the circular part with the cube part. Points divided by cube points. So then we will append those values. Now I'll define it as an numpy array. Now we'll make axis values. So I'll make a axis. X is equals to this, and for I in range, let's say 5 to 5, 10,000 for now. 10,000 and x dot append I. Now I'll just plt dot fig size, let's say 6, yeah, 10,5, let's say, and plt dot, I'll just copy from here now. Number of points by x. Okay, the sphere points is not defined because it's not sphere, it's okay, so it's sphere. Where is it? Sphere, it's not points, it's pt, yes. So then we have this, and fig size is equals to, okay, x dot pi must have same dimensions. So earlier actually it was it's dependent upon this, so we have to define it same. Okay, so you see here we have the similar plot. Okay, so it just vary along 0 to then 6 and then fluctuate more and goes lesser and lesser as the value of the beads increases. However, there is still the fluctuation you can see because the number of bead values in the 3D is 4,000 and in the 2D we defined it as 10,000. Hence, the 2D one is more accurate this time, and the value of pi in the 3D, since it is the beads are only 4,000, it is defined less. And if you try to make it like a very big number, it can make like some load over your PC also. So and it will also take some time. Now finally, I don't think you must have any doubt in this because these both things are similar to the 2D one. Just there must be some there was just one different thing. There is equation difference, and there is a new object here, which is a plt underscore wireframe, which help us to just create this sphere diagram using its equation. So if you have any query, tell me. And let's begin with the simulation stuff. So yeah. So do you have any query? So everything is fine. Yeah. So code. So last code is here. It was actually same as we have in the 2D. Just we have the formula difference here in this code. So this is basically using the same logic we use for the those things. So this is the code. I hope you have seen. If you have any query, please ask, or should I show you some part again? Okay. So now we will creating a simulation. Okay. So very beautiful simulation. I actually did it uh, a long time ago, and it was one of my very good analysis I did as a part of some part of that research. But we will be doing a simpler part of that. Now there are many things like for creating a star cluster simulation, we have different parameters. First of all, we have to define the equation of motions, Newton's laws, and uh, mass variation, evolution, etc. But today only we will be using only Newton laws and normal physics laws of gravitation, and we won't be using the evolution part and the motion of the effect of each star um simultaneously. We won't be doing that because it need good supercomputers or good servers, because more will be the code and more will be the simulated part. We need more good computational hardwares. Okay, so we will be doing what our computer can do and what we can achieve at a maximum level. Okay, so first of all, I'll create star cluster simulation. Okay. Yeah, I think this is fine. Now I'll just define everything again to make it very clean. So yeah, let's get started. Import numpy as np import matplotlib.pyplot as plt plot as plt. Now, I want you to keep in mind the gravitational formula. Okay, now which is those g m1 m2 by r square basically. I'll just show you again. Newton's gravitational law. So I want you to remember this formula. Basically we will be using this. So now we have to define the number of stars in our star cluster. Okay, so first of all we will define simulation parameters. Okay, which is n will be is equal to, let's say, 50 stars. Okay, and then I have to define the number of stars in the cluster is defined. Now I have to define the time steps to simulate. Okay, so I'll tell you what is the time step. Then we have to define the time interval between the steps also, then dt, and then we have to initialize the Monte Carlo. These are the basic things. However, I will tell you what why we are defining this and what this have effect on our simulation. So the time step and dt is equals to 0.01, let's say. Now Monte Carlo initials, which is basically np dot random dot seed, let's say 42, So random seed ensure reproducibility. Now we have to define the x and y of each stars. The shape will be n comma 2 where n is 50. So we have to position it. So random positions for stars, which will be is equals which will be positions is equals to np dot random dot uniform, and it will our matrix will be basically from 1 to or minus 1 to 1. However, we will define the range again from some distance if we need. So however, the initial thing will remain constant, like minus 1 to 1 with size is equals to n comma 2. So n is 50 comma 2 in x and y direction basically. So this allows basically to automatically define some random x and y's. Okay, so helps to define random x and y. Now we have to define the velocity. So for that we will be using something uh, random initial velocity. So it will be just initial velocity. So we won't be like taking some differentiation of those change in the distance etc. right now. So it will be just random velocity initial, which will be is equals to vx vy, and velocities will be is equal to same as this. However, we'll change the velocity to be much smaller by initials, such that it also have a, like near to zero velocity also. Now we will add some random masses because each will not make. However, some of the simulation initially when I was learning to make this stuff, we took the mass constant for all stars, but for a much more realistic look, we will also define different masses for different stars because we know how to use it. We'll use something the same here. I'll change it to masses and b dot random. Let's say the mass starts for, since the mass will be always positive, let it start from 0.5 and it goes till 2, and also it doesn't have any x and y, so it will be just n for n values. Okay, so also it will do one thing, all the stars are similar but not identical. Okay, so it make that rule follow. Okay, now finally we define a function for force calculation. Okay, so define, okay, so I'll just write defining function for force calculation, which is equal to def, let's say write a meaningful name today, compute gravitational forces comma position and mass we need it. Okay, now we will define, let's say the initial forces has the array of 0, so there is no initial force when uh, the things were getting started. So let's say the initial forces has 0 values, 0 like there is something like uh, 0 like function inside those numpy for these positions. Okay, so yeah, now we will make a loop, a nested loop, uh, to define the function, and there will be two things now. Some of the stars will have the same distance between each other. Some of the stars may have different distance between each other. Okay, based upon that, we have to define the function. Okay, so to calculate uh, those r vector. Now there is a catch in the formula. We have g m1 m2 divided by r square. where r square is the distance between the two masses, okay, for the system. This is basically an n body simulation, so you can also write it as n body simulation, okay. So where n is equals to 50, so 50 body simulation, okay. So now for that purpose we have to make sure that if I is equals to j, I is equal to j means if r1 and r2 are equal, it will make the r is equal to 0, and division by 0 can't be possible and the force can't be defined well. Okay, so there should not be, denominator should not be 0. So we have to prevent the division by 0 also. So we have to keep in mind for that also. Now let's say for I in range n, so this will be the first distance. Let's say for j in range n. So this is basically R1 and R2. We have to pair these. So why we have used these things? This is actually the nested loop. This is basically we are pairing these both things together. Okay, just like R1 to R21. That is the distance from distance of one from two, R1 to, and R2 from one, something like this. You got it actually. It's just a vector analysis. So now if I is equals to j, then continue. Then no need to do calculation. Now if not, then define the r vector is equals to positions of j minus position of I. Now the catch is here. We have write j in the first and I at the back because j is nested inside the I. If I have defined j outside I, then I have to write I minus j. So that is the thing why I have made it like that. So now I will define the distance also. Distance will be is equals to, there is a function called linear algorithm, which will find the distance automatically using these vectors. Okay, so distance between the two stars. Okay, so it will be using algorithm, lin agl dot normalization, and then r vector. So this will calculate the distance. Now there is something called softening. Softening is also very important. So it is basically used such that even if in any case there is some negligible distance that is considering that is making the division by 0, we just add a little bit fluctuation or error by our own purpose just to make sure the division by 0 is uh, there should not be division by 0. So let's define soft is equals to 0.01. So this is the intentional error we are giving. Oh yes, so this is the intentional error we are giving in the distance. So we will add distance square plus softening square, okay, in the force. Now force will be is equals to force underscore magnitude, because we have to define the magnitude differently, and we will also define the those things, what says the direction r vector, sorry, not r vector right now. We have to define g times, we also have to define g, sorry, I missed that. I mass of g, oh sorry, I masses of g divided by bracket distances, sorry, it's not distances, it's distance times to the power 2 plus soft. This is intentional so that it should not be divided by 0 intentionally in any way, even if we have skipped the we have applied this function here. Okay, now force magnitude. So force magnitude will be is equals to r vector divided by distance, of course. So basically, this is all vector analysis or vectors, basic formulas of the forces. Okay, in the vector form. So it will be direct. Now force So we will combine everything now. Let's say force I will be is equals to will be the plus mixture of magnitude force back plus force direct. Okay, now we have to return force, yes. Okay, so I have to check is it correct here? Yes, it must be something here. Yeah, aligned to this, not these values. So you have to make sure that the return force must be under the first tab. Okay, now we can also define an evolutionary loop, which will be like dependent upon acceleration. Uh, like what will be like effect of it after some dt, where dt is 0.01. So we can also that's why I use these two things. So it helps us to calculate the evolution after some dt time. Okay, so this was basically for that purpose. However, we have not since now here is catch. You can also plot the simulation now onwards before doing the evolution stuff. Plus, you can also do the evolution stuff and then plot the simulations. But there will be difference. The evolution simulation will be more like advanced work because it will be using those differential form of Newton's law, Newton's second law, which will be F is equal to ma, then the velocity v is equals to v plus a times dt, and then x is equal to x plus v dt. So we will be using all that stuff and then finding the exact trajectory also. So for that, we will write a function for evolution as well. However, there is we can't do some things like stellar evolution, and particularly for single stars, what will be the evolution and the material, because we will be required exact same data for that specific stars in the sky, because a this is a simulation and the stars we are creating is our own. Okay, so we have defined random masses, but when we do the study on star cluster, we have each and every star, and we have each data for that particular star, and their spectral properties, mass, etc. So we have to particularly input that type of data, real data, and it make the code heavier and heavier. So yeah, evolution function. Let's say trajectory for now before any evolution is null. Reject. I'll just write reject. Okay, so I'll just complete it. So okay, now for step in range, numpy dot step. So is there any problem with the visibility of the screen? Please tell me. Is there any screen problem? Okay, okay. Okay, now we will define the functions. Oh, sorry. Now we have defined steps in this range, which is basically 500. So we have just taken the 500 steps with the dt of 0.01. So we will be like multiplying and adding all this stuff in further. So now Okay, so yeah, so now we have to write 3 to 4 functions. So I'll just define here what we have to write. First of all, we have to define the uh, force function, so the acceleration, which will be is equals to force divided by mass. Then we have to define the velocity. Velocity will be is equals to, so velocity will be is equals to v plus a times dt. Then we have to define x is equals to x plus v dt. Now to make this function, we have to call this whole function now. So the forces will be is equals to, so the forces will be is equals to compute this function positions and masses, and now acceleration ACC will be is equals to forces divided by masses. Okay, and I will index this such that there is a this is just for precise function. We can like also not do this, or just skip it for now. I'll just skip it for now. I'll just add something here if needed. Okay, now velocity is equals to, will be plus is equals to ACC times dt. Then position, let's say pose plus velocity times dt. Okay, now trajectory will be will store the positions for visualization actually. So we have to append all these position and copy the position in the form of trajectory. So we have to basically, since the trajectory list was empty, so we have to append all these values. We have to copy these all the values in the trajectory. So we will first copy and append it. Now trajectory dot append, and then positions dot copy. So this is the way we do this thing. Okay, so basically here also we have to write pose copy. Okay, now finally I'll come out of this box, and now I have to make it as an array, not list. Okay, anymore. So trajectory. So now finally we will visualize the stuff. ELT dot figure, and I'll make the figure size is equals to 6,6 as usual. Then plt dot scatter will be basically, we will be plotting the trajectory with the index -1 comma, then let's say till 0. Then I'll have to do this. I'll tell you what I'm doing. Then s will be is equals to the size, actually the size scaled by the masses of the dots, which will be is equals to 10 20, let's say. Since these masses are very small numbers, it might not be visible, so I just multiplied it by some number. Then c is equals to white, color is equal to white color. Okay, it's good. Now we have to plot the trajectory also. So the trajectory will be actually those lines we have to plot. Okay, so I will plot some line connecting every like star from the center. So it's not like very important, but it will look good. Okay, so I'll just do that stuff now. Plt.plot trajectory, and now I'll create a function, basically not a function. I'll create a syntax with the I range. So it will be something like for I in range n, those number of stars, plt dot plot, then same thing here. I'll copy this. Just one thing here I have to correct is I will plot everything what's in the range. I have to plot everything. Okay, now alpha is equals to 0.5, just to make a transparency so that we can properly look at more on the star cluster rather than the, let's say, title Ars and body simulation. Okay, then plt.x label will be x positions, so it will be random. We have not defined it particularly, so it will be just, I'll tell you. So it will be like based on the trajectory. Okay, then y plt dot now. Okay, so the white want to be visual. I was like, there is a feature actually I just want to show why I made this white, because you will be have something in mind that I have made it white, but those circles will want to be visible, right? So there is a feature something called GCA, and GCA dot set face color. So you can change the background, okay, of in Matplotlib. Let's say the face color is set underscore face color is black. Okay, then plt dot axis, then equal axis. Okay, so it must be equal. So if it starts from like 500 to 1000, the another one also must be the same. Okay, so now finally plt dot show. So there will be an error, a big error. Okay, that was not the error I was expecting. It's saying 0 like don't have any attribute. Also we have not defined the value of g, so we'll fix that first. So where is the zeros like? It's the zeros like. Okay, so here, so now either there is something like we can use constant to define the accurate value. So either you can use this method, basically the last lecture, I guess, not the last lecture, the third lecture, third day, we use something. uh, okay, so third lecture is here. So we learned how to call the values like UPCs, the units. Okay, also we learned how to call the values of gravitational constant. So what we will be doing is we will be just from constant import g. Okay, so just we have to write this thing. So we will write this thing here, and I'll just import g, and there is something called positions is not defined. So okay, so I have to write positions here, not position, and then it says force is not defined. So I have to write it. I have to write forces here, I guess. Yeah, if I'm not wrong. initial forces were zeros, and then it says can only add functions to dimensionless quantities with other arguments is not a quantity. Okay, so there is an error here. It says you can't add some things here, but we okay, sorry, we have to multiply it. Another thing which is wrong here, can't store quantity with dimensions resulting from adding functions. So I have not added anymore, I guess. I have like multiplied it now, and it says we can't save this thing. So okay, I don't think there must be some error now. Okay, so this is correct. There is some function in there is some error while creating this function. 57th line, compute positions and masses. Okay, I'll just check it once. Okay, so what's the error? Can't store quantity with dimensions. Unit type error. So I have some unit error. Can't store quantity with dimensions resulting from adding function in non-quantity. So it must not be something. Okay. What if I do something like this? Okay. So just a minute. So it says we can't do this thing, right? We have the forces. Okay. So I think positions is okay here. The masses is okay. So I'll just check what's the issue. Yeah, our code is correct. Oh, sorry. Um, there must be some like can't store quantity with dimensions resulting from error. So I know there is a small like a very small error again somewhere here. Um, I'll just check it line by line again, or let's say g is equals to 1 for now. Okay, there is not an error that is created by this value. Okay, so then n is good, dt is good, then We have this good. Okay. Then we have random seed is equals to 20, 45, 42. Okay, so then we have this thing here. Okay, so this is also good. I in nested loop is okay. This is okay. This is okay. This is okay. This function is okay. So it's finally, I think it must give something. It must give something. Okay, so today was quite hectic for me. Okay, so we have something. We have something finally. So you see, we have the star cluster with these positions. Okay, and masses differently. Some are small, some are big. Okay, so there are two reasons. There are like two reasons here why the code was not working. So we were defining a very extremely like small value of g. So this whole part is very simulated. Since our masses were between 0 to 5. Just a second, guys. Just a second. It's just 2%. I have to